Next up, let's go ahead through the process of system calls in xv6. So the story here starts in the main function. Over in the main function, we called a function called tvInit. So let's go ahead and look at tvInit. That is in trap.c. And what it does is it's going to install 256 signal handlers. So when a signal occurs, this is going to install a signal handler, which is so the trap vector is an array of function pointers. And so for each of these 256 signals, it's going through and doing the setGate macro, which does stuff. But the important thing is that this vectors array here contains the signal pointers that we want to install. So we're going to install the ith function pointer into the ith signal handler slot. The one special case here is we're going to handle one that's called t_syscall. And that t_syscall is going to install the handler for t_syscall here. But whereas all of the other signal handlers are being, all the other interrupt handlers are being installed with a flags of 0, the interrupt handler for the system call interrupt is being installed with a flags of DPL user. So we have two ways of triggering an interrupt on a Intel style machine. The normal way to, or the sort of obvious way to trigger an interrupt is that a hardware event occurs, and that in hardware causes an interrupt to be triggered. The second way that an interrupt can occur is a software interrupt. There's a assembly instruction that is the int assembly instruction, and that int assembly instruction can be written in assembly code. We give it a number, so we could say like int 5, and when the int 5 instruction occurs, that'll cause the CPU to act as if interrupt number 5 had occurred. But there's a security issue there. If for example, say interrupt 5 was the disk controller, and so if we trigger interrupt 5, that's going to cause the CPU to go engage the disk driver and try to read something from the disk or something. We don't want users to be able to randomly cause that to happen whenever they want. So every one of these interrupt handlers needs to have permissions associated with it. By default, only the kernel can trigger an interrupt, but if we explicitly flag it with this user flag, then that means that all code can trigger the interrupt. And so there's one interrupt here, the system call interrupt, that users can trigger at any time. The reason we need that is because traditional 32-bit x86 didn't have a syscall instruction. And so instead, this interrupt instruction is used to trigger system calls. On Linux, this was always interrupt OX80. Here on xv6, it turns out that I'm not in the right tab. grep t syscall star.h. Our interrupt for system calls is integer 64, which is not interrupt OX80. Those are different numbers, but to do a syscall here, we do int 64. Now to follow this plan through further, we have to go find this vectors thing in order to do that, and that lives over in a file called vectors.s. So vectors.s has this comment in it that says generated by vectors.pl, do not edit. Makes perfect sense. You don't want to write assembly code by hand, instead you write a Perl script to do it. And that's especially true for this particular piece of assembly code because there's a pattern here. we have a label, vector 0. It's going to push the number 0. Well, it pushes two numbers, but one of them is the number 0 onto the stack. And then it's going to jump to a thing called all traps. Same thing with vector 1. We're going to push 1 and jump to all traps. Vector 2, we push 2 and jump to all traps. Vector 3, we push 3 and jump to all traps. There are 256 of these, 0 through 255, all doing exactly the same thing. And then the vectors array itself is just this list of assembly constants, which is just this set of function pointers up here. So these labels are what's stored in here. So no matter which interrupt occurs, what xv6 does, it's going to push the interrupt number onto the stack, and on 32-bit x86, that's the same as setting a function parameter. All function arguments are passed on the stack, and then we're going to jump to this all traps thing. So let's go look at all traps. All traps is in trapasm.c. Sorry, trapasm.s. So all traps is going to save some additional information onto the stack. We're then going to mess with data segments a little bit. This is preparing to do the context switch from user space into kernel space. We're pushing some more stuff. And finally, we're going to call this trap function, which is going to actually handle this interrupt. The trap function lives over in I'm assuming trap.c. Yeah, here's our trap function. It's going to take a single argument, which is the struct trap frame. Now, if we look back over here, we can see that the thing that we pushed onto the stack before we called trap was the stack pointer. And again, the way functions get arguments is by taking things that were pushed to the stack. So the one argument to this function is a struct trap frame. And it turns out that a struct trap frame is the thing that we were building as the result of pushing things to the stack here in this assembly. This is slightly tricky and clever, but if you go look at the definition for struct trap frame, you can see what's going on, and this code does in fact fill that in correctly. Most importantly, when in the vectors file it pushed the number of the interrupt onto the stack, that ended up lining up in memory with this trap number field in this trap frame that we're getting. And so we're able to have different behavior depending on which interrupt occurred. The interrupt that we're mostly interested in is the system call interrupt, which will let us go ahead and do the syscall function, which implements all system calls. But it's interesting to also see in here that we have a bunch of stuff for other interrupts that could occur, like the timer interrupt, which times out processes if they've run for too long and gives the opportunity to schedule another one. We have our IDE interrupt, that's the hard disk, simulated hard disk. We have this thing, which is a implementation detail of a simulator that we're not using. Here's our keyboard driver, here's our serial driver, and then if some other unexpected interrupt happens, we're going to kernel panic. So all the things that we handle are like keyboard, console, serial, hard disk, timer, and then system calls. So the next part of this story is over in syscall, which I bet is in syscall.c. And what the system call function does is it's going to look at the trap frame, which got stored in this current proc thing as a result of the trap setup. And in that trap frame, we have the saved value of the EAX register. Now you'll remember that the way we did system calls on AMD 64 is to set the RAX register to the system call number. It's the same thing on 32-bit, except we don't have R registers. The biggest registers are E registers, the 32-bit registers. So the system call number is going to be in the EAX register when we get in here. And so this is then going to look that up in the system call table. And conveniently for us, the system call table is this table right here. So this is going to map our system call numbers over to the functions that implement system calls. So if we want to add a system call, what we have to do is we have to fill in all the places where some existing system call gets used. Now there's two good system calls to look at. A system call that I added to xv6 is this halt system call. Halt is not provided in the default xv6 that MIT distributes. We need it for the automated tests, so I put it in. Another good system call is uptime. It's a nice simple system call that just prints how long the machine has been booted. And again, it fills in all the places where it's required to do a system call. Another good one to look at is the fstat system call, because that requires filling in a structure, and that's something that you have to do in the homework. But for this, we're going to go through and look at all the places where the halt system call was implemented. So to start off, to add a system call, we have to look at syscall.h. And this is where we specify system call numbers. So you can see here, xv6 came by default with 21 system calls. To add a new system call halt, I added a new preprocessor constant for the new system call, and I assigned it a number. Halt is 22. If you want to assign more system calls, the next one's probably 23. Although, logically, I think you could skip system call numbers if you wanted to deal with how to fill in the array properly. Once you've set a system call number, the next thing that you want to do is back in syscall.c, you want to make sure that you've set a declaration of the implementation of the system call here. So system call implementations all have the signature, a function that takes nothing and returns an int. And then once we've declared that here, we then want to reference it in this system calls array. And again, if you're adding a system call, it probably just goes here on the line after syscall halt. Next thing that we need to do is actually implement the system call. So the implementation of halt lives over in sysproc.c along with a bunch of other system call implementations. We can see that fork is in here, exit is in here, etc. Our halt system call is down here at the bottom. And the implementation here for halt is that we're going to do an IO port output. IO ports are sort of an obscure way that software can talk to hardware. They're not terribly efficient, but it happens to be the way that we shut down our computer when we want to have compatibility with the QEMU virtual machine. Tracking down this particular incantation was actually kind of fun. There's not a lot of documentation on how to interface with modern IBM compatible style PCs. And in fact, there are implementation, like this is a homework. Implementing halt is a homework in the old MIT course. So intentionally, they didn't publish how to do it. But there's a couple of implementations of this on GitHub, and they have the wrong thing. They don't have the right numbers that you have to pass to outw here. I then looked at another teaching OS called Pintos, and it also had the wrong answer. So I ended up having to go look at Redux, which is an experimental operating system that people are working on built entirely in Rust. And I guessed and was correct that since they're currently doing operating system development in the current version of QEMU, they'd get the right incantation. But we have to send this message to output port OX604, and the message that we send is this, and that will cause the machine to immediately shut down. I have this while one just to make sure this doesn't return. I'd rather have it freeze up and not execute any extra code if it takes a second for the shutdown instruction to actually occur. And that's actually the entire implementation of halt, because halt is pretty simple. And that's actually all we need to do in the kernel, but there's still another couple things that we need to do. We need to make it so that this system call is accessible from user space. Usually that involves putting a C wrapper that actually does the system call. And in xv6, we have some helpers to let us do that. So all of the system calls and actually all the C standard library functions for xv6 user space programs are declared here in this file called user.h. Most of these have a sort of the same system or the same signature as the implementation. They take nothing and return an int, but that isn't necessarily the case. There's some other signatures in here. So here we are saying that halt returns an int. Halt never returns. It always shuts down the machine, but we might as well say it returns an int. Then we need to make sure that it is actually the assembly code that implements the system call. We need to make sure actually gets generated. So let me quickly find that. It lives in usys.s. Here we have this C preprocessor macro that's going to implement a system call by moving the system call number to EAX and then doing the system call interrupt. And then we call that macro to define all of the system calls in the system. And so I had to add halt to the end of the list here. So that is the stuff necessary to make it possible to call this system call. Then we need some sort of test program to make sure that we can actually do this thing. And in this particular case, that's pretty easy. I actually want a executable file named halt, so we have a halt command. And we're going to make sure that we include user.h, which defines our new system call wrapper. There's some other headers that we just end up with in xv6 user space programs. And then our function, or our program, just calls halt as the first thing in main. And that gives us our shiny new program that uses our shiny new system call. So let me demonstrate this exciting process again. We're going to start up xv6, make qemu nox. Then we're going to run our halt program. So this is a file that exists on the virtual disk. It's executable. We type in halt. It's going to run that program. That'll then interrupt 64, look up the interrupt number 64 in the system call, or sorry, in the interrupt vector. That is going to then call the system call function, which will look up system call number 22 in the system call array. That'll call this code that does that output. That results in the computer shutting down. If we had installed this on a physical computer, we could install xv6 directly on a computer. If we had done that, it would shut down the computer. Since we're running it in this QEMU simulator, it shuts down the virtual computer. And that is our sequence for implementing a system call. Let me go ahead and pull the assignment over real quick, just so that we can make sure that we see the moving parts here. So let me grab it and bring it over. So here's our assignment. So what you're supposed to do is you need to install the prerequisites, things like QEMU, so you can actually run the xv6. Then the system call that you're adding is a system call called getIOstats. What this is going to do is it's going to get the total number of bytes read and written for a file descriptor. So that's going to require that you figure out what the data structure is for a file descriptor in xv6. We talked about the open files, the file descriptor table that every process must have as part of its process state. Definitely I recommend going and looking at the stat system call, because that deals with some of the same stuff. And then you're going to pass it a file descriptor and a pointer to a struct. In the implementation of the system call, it's going to go ahead and look up where it's going to find this data. And it's going to fill in this structure. There's the struct right there. And then in order to get that to work, you're going to have to do all of this stuff. You're going to have to go add some fields to the structure to keep track of this data. You're going to have to modify some of the existing system calls to make sure that those stats are being updated. You need to add the new system call using the process that we just went through. And then you're going to need to add this struct iostats structure so that it's accessible to the user programs. Now, in the starter code, we have 3 C programs which are tests, and they're not built into the xv6 image by default because they won't compile, because they depend on a function that you haven't written yet. So you're going to want to look at the makefile in the xv6 directory, that's this makefile here, and figure out what's going on in here and why there's a uprogs list, and you're going to want to add those programs to that list. Finally, do some manual testing, make sure that your thing works. Run the automated tests as usual. You can do that from back out here, perl test.pl. It's like compiling xv6 or something. Maybe it's just frozen. Oh, okay, it was waiting for the programs to execute, and they aren't there, so they never executed. But we have a lot of failures. But once you actually implement the system call and re-enable the test programs, you will get less failures. And for this, you definitely want to make sure that you type make clean, because xv6 is pretty big when it's built, and make clean will clean that up. I think that's mostly the whole story. So yeah, we'll see if anybody has any questions in the discussion either tomorrow, or since I don't trust that everybody will actually have watched this video before the discussion tomorrow, maybe there'll be questions on it on Friday. Good luck finishing up the current assignment, and good luck getting started on this one.